These products are derived from our foundational base products, reflectivity and velocity, using known meteorological relationships. Before we get started, we must go over one important caveat when using these derived products and algorithms. Some of you may be aware of composite parameters in severe weather forecasting, such as the significant tornado parameter, or STP. STP attempts to boil down the incredibly complex set of ingredients needed for significant tornadoes into one number. While it can be a quick and easy way to get a broad overview of significant tornado potential, it completely ignores many of the intricacies that may arise in a given environment, and therefore should not be used as the crux of a forecast or storm-chasing decision. The same holds true for derived radar products and algorithms, which are not directly measured by the radar, and instead are mathematical manipulations of the base radar products. Every derived product and algorithm has inherent issues in how its output is calculated and uncertainties in the end product. Therefore, they should not be used on their own to make nowcasting decisions. Instead, they should be used as a tool within a broader toolbox of radar products to effectively analyze severe storms.
Seats are currently on sale for our 2027 Storm Chasing Tour. Secure your seat now for this once-in-a-lifetime experience. Link in the description.
Let's dive into the main derived products and algorithms you might use when out in the field. Let's start off with perhaps the simplest derived product, which is composite reflectivity. Composite reflectivity displays the highest reflectivity value within every vertical column of bins or pixels, regardless at which elevation angle it occurs. It can work well when monitoring for storm initiation, as precipitation droplets or ice crystals can initially develop at a much higher elevation angle than the lowest tilt. In this case, the composite reflectivity product may show robust returns well before the base reflectivity product shows anything at all. In addition, composite reflectivity is useful in situations in which the radar beam is blocked by terrain features or other objects, a problem in places like Southern California, Southern Arizona, and New Mexico, among others. Really any radar site that's perched near or in the mountains. The radar beam at the lowest elevation angle, or even multiple elevation angles, can be blocked by mountains, leading to a lack of echoes even when storms are ongoing. The composite reflectivity product can combat this because it displays the highest reflectivity value within every vertical column, which neglects the elevation angles that are plagued by beam blockage. For example, a strong thunderstorm was ongoing north of Roswell, New Mexico at the time of this base reflectivity image from the KHDX radar, but you might not know it. The KHDX radar is completely blocked in the low levels to the east by the Sierra Blanca Mountains, rendering the lowest two elevation angles useless. When we switch to composite reflectivity, we can much more clearly see the robust precipitation associated with the storm in question. Composite reflectivity does have its drawbacks, however. If the radar you're using does not suffer from beam blockage issues, composite reflectivity should not be used in lieu of base reflectivity, as many important storm features, such as hook echoes and boundaries, are easily masked by stronger reflectivity values at higher elevations. For instance, on the left is a base reflectivity image of a tornadic supercell with a very well-defined hook echo. On the right is the same supercell displayed using composite reflectivity, and as you can see, the storm just looks like an amorphous blob of precipitation with no evidence of a hook echo. Also, composite reflectivity tends to overestimate the quantity of precipitation that may be falling at the surface. The next derived product is called vertically integrated liquid, or VIL. The VIL product estimates the liquid water content in each vertical column of radar data by integrating the reflectivity values at all elevation angles in each column. Therefore, VIL is a good indicator of heavy precipitation in convective storms, with higher values representing heavier precipitation. VIL is a measure of mass per unit area, with units of kilograms per meter squared. Many chasers utilize VIL to determine whether or not a storm is producing hail, as well as how big that hail is. Because larger hailstones correspond to higher liquid water content, high VIL values can suggest that large hail is occurring. However, this practice is not entirely accurate, as VIL on its own is not a great tool to use to identify hail-producing storms. There are several reasons for this. One, VIL values depend on the characteristics of the air mass in which the thunderstorms are occurring. For example, storms in colder air masses may produce severe hail but still have low VIL values, while storms in warmer air masses may yield high VIL values but not produce severe hail. On the same token, because VIL is an integration of reflectivity through the depth of the storm, shorter storms tend to have lower VIL values than taller storms. This makes it difficult to distinguish between shorter storms with high reflectivity and potentially large hail, and taller storms with low reflectivity and no hail. Also, VIL values in storms that are quite close to the radar site are underestimated because the upper portion of the precipitation core may lie above the highest elevation angle of the radar. The same issue occurs in storms that are at the edge of the radar's domain, as the lower portion of the storm may be neglected. Finally, VIL can be significantly underestimated in storms whose updrafts are tilted, which happens in environments with strong vertical wind shear. VIL assumes that all the precipitation in a vertical column will fall downwards solely within that column. In environments with strong vertical wind shear, this is not the case. A storm's precipitation core would be tilted rather than mostly vertical, and therefore cannot adequately be sampled. Storms that move quickly enough to displace the upper portion of the storm significantly before a full volume scan can be completed may be associated with underestimated VIL as well. Because of all these issues, VIL must be used with dual polarization products to accurately assess large hail potential in a given storm. National Weather Service radars calculate two versions of VIL: traditional or legacy VIL and digital VIL, which is most commonly used today. Digital VIL was developed to deal with some of the aforementioned issues of traditional VIL. With traditional VIL, reflectivity values within each vertical column are truncated to 56 dBz to reduce the impacts of hail on the output, so any reflectivity values that exceed 56 dBz are reduced to that value. Digital VIL does not truncate reflectivity values, so it often yields a more realistic output. Also, digital VIL utilizes a more favorable coordinate system than traditional VIL. While digital VIL can provide more realistic outputs than traditional VIL, it still suffers from underestimation in situations with highly tilted updrafts and storms that are moving quickly. Thus, it still should only be used in tandem with other products to determine large hail potential within a storm. Our next derived product is the EchoTops product. The EchoTops product gives the maximum height of precipitation echoes detected by the radar that exceed 18 dBz between 5 and 70,000 feet above radar level. In essence, it estimates the height corresponding to the top of an area of precipitation, and it can be a decent proxy for how tall developing or ongoing thunderstorms are. The greater the EchoTops value is at a given point, the taller and stronger the updraft or storm is. EchoTops can help you monitor for convective initiation and can tell you which storms in a batch of storms are the most robust and may hold the greatest severe weather potential in the near term. A sister product to EchoTops is Enhanced EchoTops, which helps smooth out irregularities that can sometimes appear in EchoTops output and identifies areas where the radar could not compute a cloud top height. Its cleaner output makes it much preferred over the traditional EchoTops product. Let's now move on to some algorithms you may find useful when chasing, the first of which is called the Hydrometeor classification algorithm. This product uses a multitude of other radar products in an attempt to determine the predominant type of target, or hydrometeor, within the radar beam. The range of outputs runs the gamut from non-meteorological targets, such as birds or insects, to snow, rain, and hail, the latter two further separated by size or intensity. Hydrometeor classification can be a bit of a cheat code to identify precipitation type. However, you must remember that it determines the precipitation type at the height of the beam at a given location, which may not always be the same as what you might experience at the surface there. For example, it may identify hail at the height of the beam, but it may subsequently melt, reaching the surface as rain. A variation called the hybrid hydrometeor classification can also be used. It utilizes the relationship between reflectivity and precipitation rate to more effectively define the dominant hydrometeor within the radar beam. Both the hydrometeor classification and hybrid hydrometeor classification algorithms should be used in tandem with other radar products, namely the dual polarization products, to get the most accurate assessment of precipitation type in severe storms. Our next series of algorithms can help you identify important features and behaviors of storms. These are built into all National Weather Service radars, but not all radar software programs display them. The first of these is the Storm Cell Identification and Tracking Algorithm, or SCIT. SCIT identifies areas of precipitation that constitute actual storms whose basic attributes are calculated, such as maximum reflectivity value within the storm cell, probability of hail, and probability of severe hail, among others. Each storm cell is given a letter number identifier such as A1. In addition, SCIT can extrapolate what the storm's track might be for the following 60 minutes, including speed and direction. For new storm cells, this is estimated using the average motion of all cells in the radar domain or from environmental information. Keep in mind that the storm track does not apply to mesocyclones and tornadoes, but rather solely to the storm's precipitation core. If errors in the storm track are calculated, the storm track will be truncated from 60 minutes down to 45, 30, or 15 minutes, depending on the magnitude of the error. So if you come across a shortened storm track, know that uncertainty exists in that storm's track estimation. Also, SCIT tends to perform better when storm cells are isolated rather than embedded within a large complex of storms. Modern radars also feature the Mesocyclone Detection Algorithm, or MDA, which analyzes data for rotational patterns meeting specific criteria for size, strength, vertical depth, and duration.
Seats are now available for our 2027 Storm Chasing Tour. It's 8 full days of storm chasing, and the coaches on this tour are Trey Greenwood, Cameron Nixon, Kyle Gillette, and Hunter, folks. It is a lineup filled with absolute all-stars, and if you've ever wanted to go out storm chasing but you're not quite sure, or if you're just looking for a once-in-a-lifetime experience, this is definitely something you'll want to check out. Click the link in the description below for more information.
The MDA detects rotation on the order of 1 to 10 kilometers, which corresponds to a supercell's mesocyclone, and it calculates variables relating to the intensity and potential track of the mesocyclone. In most radar programs, mesocyclones detected by the MDA are identified with a circle. Color schemes for mesocyclone intensity may vary based on which radar program you use. Typically, green circles indicate weaker mesocyclones, while red and purple circles indicate stronger ones. Some radar programs differentiate between mid-level and low-level mesocyclones as well. For example, Gibson Ridge software uses a dashed circle for mid-level mesocyclones and a more solid circle for low-level mesocyclones. The Tornado Detection Algorithm, or TDA, is meant to detect tornado vortex signatures or rotation with a scale less than 1 kilometer. It works in much the same way as the MDA, but the TDA specifically looks for gate-to-gate shear, which is the shear between two adjacent pixels of velocity data, one inbound and one outbound, across a radial. To register with the TDA, the depth of the tornado vortex signature must be at least 1.5 kilometers, with its base at less than 600 meters above the surface, or at the radar's lowest elevation angle, or else it's deemed to be an elevated tornado vortex signature. Elevated tornado vortex signatures represent tight rotation aloft that can eventually develop into tornadoes. In most radar programs, a color-filled, downward-pointing triangle is used to represent tornado vortex signatures identified by the TDA. A hollow downward-pointing triangle is used for elevated tornado vortex signatures. Gibson Ridge software also provides a number within the triangle that represents tens of knots of radar estimated delta V, so in this example, the 13 inside the triangle would mean a 130 knot delta V. The TDA does have some drawbacks. It requires a full volume scan to be completed, which can take as long as 5 to 6 minutes. This can significantly delay the detection of a tornado vortex signature. Also, it does not detect anticyclonic tornadoes. Finally, radars can analyze storms for hail using the Hail Detection Algorithm, or HDA. The HDA calculates a number of probabilities and quantities by searching for reflectivities greater than 45 dBz above the freezing level, which is the level of the atmosphere where the temperature is 0 degrees Celsius. The higher these 45 plus dBz values exist above the freezing level, the greater the probability of hail, or POH. The probability of severe hail, or POSH, is related to how high these high reflectivity values are relative to the 0 degrees Celsius and negative 20 degrees Celsius levels, and tells us the likelihood of hail in excess of 3/4 of an inch. This is the old National Weather Service threshold for severe hail. Note that the current threshold is 1 inch. The maximum estimated hail size, or mesh, is also calculated. The standard symbol for hail identified via the HDA is an upward-pointing triangle. Gibson Ridge software lists the hail size in inches within the triangle, and a larger triangle is used when a probability of severe hail exists. The HDA works best when a storm is between 35 and 70 miles from the radar site. Outside of this range, the HDA's efficacy decreases. All of these derived products and algorithms should be used with caution and in tandem with other radar products to get the clearest picture of what's occurring within storms. In particular, the mesocyclone, tornado, and hail detection algorithms often produce false alarms, so using them alongside the suite of base and dual polarization products will lead to a much more accurate analysis. Also, not every radar program will have these derived products and algorithms available to you.
Remember to check out those links in the description below, and then watch another video.